Hello, everyone. Thank you for joining us today. I'm Noah Shartoff. As always, I'm joined by my host, John McNally. Here we are both Wolfram employees, education backgrounds, myself in mathematics and John primarily in physics. We're joined today as well by Jason Sonnenberg, who is our head designer for chemistry educational materials here at Wolfram. And of course, we are joined by Joshua Schrier, who is here to talk to us today about a lot of things that he is doing with Wolfram Technology in the study and teaching of chemistry. So, Joshua, why don't you tell us a little bit about yourself, introduce yourself, let us know your background, your research, what you're into, just anything you'd like to tell us.
Absolutely. Thanks. And yeah, I'm really pleased to be here. I enjoy using the Wolfram technology for lots of different things, both
Excellent.
in the teaching lab, in the research lab, and just for fun. So, just to give you a little bit of background on me, I'm a theoretical physical chemist. So, as I like to say, that means that I really only understand two and a half things: quantum mechanics, thermodynamics, and kinetics is kind of half of a theory, right? We can derive
Huh.
it from the first two. But what we do is that we use our understanding of those physical theories and use computer simulations to help us simulate chemical phenomena, right? And these
Wow.
could be chemical phenomena related to how materials, the structural properties of materials, right, or their reactivity, or how they interact with light or with electricity. And so, my background is doing that sort of traditional computational chemistry work where we simulate things. But about 7 or 8 years ago, I got involved in machine learning, and in particular, trying to develop machine learning models that were helpful to people in an experimental laboratory that were trying to synthesize new materials. And so that's gotten really popular, and so that has kind of taken up a lot of my work. I mean, if you do the Google Scholar sort by date, you can see that the kind of all the recent things that I've been working on have been kind of focused on this area of machine learning.
Now, so for viewers of ours who might be more familiar with chemistry than machine learning, what does machine learning mean in this context?
Yeah, so I mean, we use lots of different types of approaches. The early work was really sort of supervised machine learning. So we were interested in this problem of given a chemical recipe, right, a
Mhm.
set of ingredients, a set of reaction conditions and amounts, can we predict what the outcome will be? And you could think about a hierarchy of types of things that you might want to try to predict. I mean, the lowest level on that hierarchy is just like thermodynamically, can a reaction occur?
Mhm.
And then, higher up on that hierarchy might be, well, what are the types of structural arrangements that result, or what are the properties that result? And so, the kind of our beginning forays into this were really motivated around how do you get data about experimental work? And it
Mhm.
turns out that a lot of that data is just not published, right? I mean, all the failed reactions and even the marginally successful reactions, are just not present. And so,
Yeah, I've heard that referred to as the file drawer problem, that the only things
yeah,
that get published are the ones people found really interesting. And maybe there's a lot
yeah.
of data that shows a lot of things that didn't actually make it into the field.
That's right. And if you think about using this for a supervised machine learning approach, right? If you just provide a series of positive examples from the chemical literature, right? This recipe worked, this recipe worked, this
Hmm.
recipe worked. Well, it's very easy for your supervised machine learning model to then just say, well, everything works.
Right.
Right.
Yeah. Yeah.
So what we did back in this paper in 2016 was essentially we paid undergraduate students to go through a decade's worth of old laboratory notebooks and digitize them. And then, we built what are in retrospect very simple machine learning models, right? Just simple SVM models, right? The type of thing that you could do using the classify function in Wolfram language. And we found that those very simple models were actually just as good, if not better, than expert chemists at figuring out what reaction conditions to try. And the thing that we did that was really kind of fun was that we closed the loop on the process, which is to say we actually had students go into the laboratory and perform reactions, right? Reactions that human experts would specify, and reactions that the machine learning model had specified. And so that's, become now something that is a lot more common. But when we got started, I mean, we were really just kind of fumbling around. And even this idea that you needed, I like to call them the dark reactions, right? I feel like the physicists have all these great names like dark matter and dark
Mhm.
energy. So, we need a little bit of that spice. But the value of those sort of unpublished failed experiments, right? That, as you said, otherwise linger in a file drawer, but are really valuable for improving
Mhm.
the quality of your machine learning models.
The
So yeah,
machine learning,
oh,
I
go
was just
ahead.
going to say, the machine learning effort reminds me of the expert systems that were so popular in the pharmaceutical industry before machine learning existed, and they were, trying to predict based on a variety of collections of data.
Yeah, that's right. And if you think about it, those efforts, I mean, go back to the late 1960s and early
Yeah,
1970s.
they
I
go
mean, it's
very way back.
right to sort of the beginning of that sort of good old-fashioned AI. And so, this is a field now that has become really well established, within the American Chemical Society and the Materials Research Society, right? This idea of data-driven chemistry and materials research.
Mhm.
And so it's been really fun to kind of grow up alongside that field.
Yeah.
Um, so getting back to your question, Noah. So I mean, that early work was really about, sort of supervised machine learning, the types of things that you
Mhm.
would use using, for example, predict and classify, in the Wolfram language. More recently, we've been experimenting with different types of generative approaches, right? Things like generative adversarial networks, and kind of other generative models for trying to design experiments. And so that's, sort of kind of work in progress on different fronts.
Interesting. I mean, I think within the last year, a lot of people have gotten very familiar with generative AI like ChatGPT. We're used to AI that creates something, but it
Yeah.
sounds like a lot of this was about getting AI to, for one thing, understand or at least categorize things, and also to predict based on that information.
Yeah, that's exactly right. So I'm actually on sabbatical this year. So this is on the left is what I looked like before the sabbatical, and this is what I look like during the sabbatical, or maybe just right before the sabbatical. But kidding aside, yeah, I mean, generative AI and in particular things like large language models, right, have become tremendously popular. I mean, there are articles in the New Yorker magazine or the New York Times
Yeah.
about these types of things. So it's reached a broad audience.
Hmm.
But they're also an emerging field of research in science, right? This is actually a kind of a recent open access paper that a whole bunch of people did, right? Where they had a hackathon on how could you use LLMs to maybe transform material science or chemistry research. And so there are a lot of really neat examples that are in there, including my former postdoc, Qinshan Ai, right, is the second author on there. Really kind of neat story. I have to admit, it's not something that I really have played around a lot with until
Hmm.
this past summer, right, in August. And so one of my goals during the sabbatical is really to play around a bit more with large language models and these other types of emerging generative approaches. Try to understand them a bit more, and then also see how we can apply them to chemistry, right? And there are people that have started off these efforts, right? There are a lot of kind of nascent things that are out there, but really a lot of exciting opportunities. And so I think the explorations that we're going to talk about today are in part, my efforts to try to get up to speed on what people are doing, and then try to put them to use, right, in problems related to chemistry, problems related to my own chemistry.
One of the things I like about some of the community posts that you've done recently is that it sort of touches on both things that people can mean when they say using large language models for science. So one thing they could mean is using things like GPT-4 and other things that are pre-trained with a lot of language, and so they can help with the coding process. But then there's also this other question of, can some large transformer-based model that doesn't necessarily have anything to do with natural language, but could that also be helpful just as a machine learning tool for these research areas?
Yeah, that's right. And and I think it's really kind of fun to kind of explore both of those angles, if you will. Because certainly, I mean, you can think about lots of problems as involving linguistic tokens of some kind, or but those linguistic tokens are not necessarily the same ones that ChatGPT has been trained on. And perhaps another thing that comes to mind in this effort, there, I can dig out the link later on, but some folks at the U.S. Department of Energy actually have a really nice website and report on AI for science, energy, and security that just came out this past fall. But that report really unpacks some of those different ways of applying generative AI to science problems, and they range from maybe we need to train foundational models on scientific literature, or maybe we can train foundational models on numerical simulation codes, right? That are used at the different Department of Energy labs. But also, what are maybe fundamental algorithmic ideas that can be repurposed and developed to really help us understand matter and energy at all of its length scales.
Very interesting. I hope that they're taking into account the sort of thing you were talking about before, where published literature may not be the be-all and end-all of data that represents the actual world, but it does sound like a fascinating project. By the way, when we're referring to posts on community, we're talking about community.wolfram.com, where Joshua has some fantastic materials, and a lot of other people do too. By the way, if any of this stuff in the notebook is going by faster than you are following, don't worry, we are going to post this whole notebook linked to a permanent version of this interview in the YouTube location that it's going to be once it's over. So you'll be able to return to this later on.
Yeah, and thanks for that clarification. I mean, actually, maybe this is a good chance to just pivot into some of those community posts, right?
Let's do it.
And thinking about these things. So again, as Noah was saying, right, you can kind of find this post on community.wolfram.com. This was a community post. I'd actually written it up as a blog post, and it was really an answer to a Mathematica.StackExchange question that was posed. And I love just hunting the Mathematica Stack Exchange for interesting questions and a chance to sharpen your sword.
I'm a huge fan of the Stack environment as well. I'm on there every now and again. It's just a great community.
And so user 5601 had a question, right, where he or she was asking whether there was a way to get the OpenAI API to summarize documents that were longer than the input limit. And this was actually something, I guess this was back in August. And so the input limit at that time was about 4,000 tokens, right? So that's kind of roughly speaking about 2,500, 3,000 words. And so then the question is, how can you kind of expand around that? And so I guess just as a useful note for the listeners today, certainly that context window has expanded a lot.
I believe it's around 16,000 now. Yeah.
Yeah, that's right. And there are even sort of preview versions that are like at 32,000, right?
But even with 3-4 page documents, I've run into the limit. So I find this sort of thing still very relevant.
Yeah, right. And so yeah, I mean, it just kind of increases the the size of the chunk that you need to start working on. So this was something, again, as just somebody that was trying to learn this field, I didn't really know any of these methods. And so, but I thought that given all the great LLM functionality in Mathematica 13.3, that I could figure it out, right? And so I did a little bit of research and tried to find out what people knew, and found this post by Isaac Tam, right, that had been written a couple months earlier, where Isaac was describing 3 different strategies for text summarization in LLMs, essentially like summarizing things that were in the literature. And so that was really sort of my model for trying to think through it and try to implement those strategies. And so what Isaac did was he said we need some sample text. And so he picked the most recent State of the Union address, right? It's posted on his website. And so, of course, it's easy for us to just import it from his GitHub user content. And a thing that Isaac did that was really just useful for us is he broke up each of the sentences into a separate line in this document. And so just a kind of an import as a list gives us each of those individual sentences. There are a few blank lines, so I just deleted the blank lines, right? So now we've got a list of sentences, right? That each entry in this list is one sentence in that State of the Union address. So the first thing that you might try, the first thing that I was curious about was whether we could just use the prompt repository to do this, right? And so, we could actually try it, right? Like, let's use LLM summarize, right? I'm going to live dangerously and just try to run this one live, right? So we look up the resource function and then run this, right? We're just joining the strings together, and we get that error token, right? That we've exceeded the token length, right? Now, what's really interesting though is that actually there is a function on the prompt repository called summarize URL content, and that actually does do the trick, right? And so I think behind the scenes there's some server-side tool that is being called, and that is
actually. Yeah, in
go
fact,
ahead, John.
So in the prompt repository, it is actually possible. You can download the definition notebooks from things in both the prompt repository and in the function repository. And so if people are ever curious about like what are the actual prompts or what are any of the pre or post processing that's going on into any of these things, it is actually possible to check. I know I haven't looked at it this week, but I know in like the very first iteration of this, one thing that you would sometimes do to avoid hitting context limits is just take the certain first part of a document, and that's like an easy first trick to do, right? Since a lot of the important stuff might be in the beginning. But yeah, if you're ever curious about any of these things, you can download versions from the repositories directly.
Yeah, that's a really great piece of advice. And for those of you that are looking at the notebook later on, I've included a link as well that'll take you there. But somehow it works. I guess that's cool. It also seems too easy. So I guess like in the interest of trying to understand things by building them up, we could explore some of those techniques, right?
Mm-hmm.
So one of the approaches is this approach called recursive summarization, right? And so the idea is we just break up the text into short chunks. Each chunk fits within the LLM window,
Sure.
right? And then what we do is that we summarize each chunk independently, right? So it's sort of like if you took a book, you rip it up into pages, you summarize each page, and then you concatenate the summaries of each page together and make a summary of the summaries.
Oh, okay.
So that's kind of a neat way, right? I mean, one advantage of this is that it's really easy to parallelize, right? So, you can dispatch all of those independent summaries of the smaller chunks, get the list of chunk summaries, right? And then it's just kind of one shot to summarize it again.
Which a human couldn't do. They couldn't read each page simultaneously, but the computer can. So
yeah. Well, if they had enough time and enough coffee, I suppose they could do it. So one thing, however, is I've noticed that actually it seems like the default settings are to use GPT-4 for more and more things. And so actually, one modification from the community post is that I've added in this LLM evaluator option that just forces us to use GPT 3.5 Turbo instead, right? So this will give us results that are like a little bit more comparable to what we had before. It'll also save a few pesos, right? Because the GPT 3.5 calls are just a lot cheaper.
Plus, you want to be using the most accessible of tools to see whether or not this method actually works for them.
That's right, and it becomes a lot less expensive to experiment, right? If you do that. So just as kind of a tip for the readers, right? That's something to keep an eye on. Yeah. So basically, our chunking is not too hard to think about, right? We have our list of sentences, right, that we downloaded from the web, and maybe just a parameter to define the chunk size. I'm doing this based on word counts, which are not exactly the same as the tokens, but it's just practically easier to think about it.
Am I correct in remembering that a token tends to be more like a part of meaning, like a suffix or a prefix, or it can be an entire word, but it's usually just whatever part means something within.
Yeah, that's right. I mean, there's a little bit of special sauce in developing a tokenization, but yes, that's the right idea. So some words like happening might be broken up into happen and ning, right, as kind of separate tokens. On average, the sort of rule of thumb is that it's about like one word is like or a token is about 3/4 of a word. Just as kind of like a rule of thumb. There's a tool called Tick Token, that is provided by OpenAI that will actually pre-count your tokens. And in fact, there's a tool on the Wolfram function repository that will count tokens for the GPT-2 model. But the tokenization in GPT-2 and GPT-3 and above is different, right? So I mean, so it kind of gives you some estimate, but it won't be exactly right. Yeah, so I guess there's some nuance, but you're absolutely right, Noah, right? A token is like it's often a piece of a word, although simple words like note, that, as, Wolfram are probably just individual tokens. Yeah, so basically,
and I believe you've also done some. Oh, sorry. I was just. I believe you've also done some really interesting things where you've actually fitted a linear model to check what the average thing per token is, which I love when people do that sort of thing.
That's right. So when I was first playing around with this, I was trying to do some retrieval augmented generation, and I mean, that was kind of my first foray into doing this. So I didn't really know what it was, but indeed, right, you can kind of take word counts and token counts. And fit your own linear model to try to figure out what that is. This is all based on the GPT-2 token counter that is on the Wolfram function repository. So yeah, I mean, it's kind of a fun thing to play around with. And this particular corpus that I was playing around with, had a bunch of shorter documents. It had a few documents that were just too long. And sort of based on this, you could figure out a reasonable place to just split things and divide them into smaller chunks.
Very cool.
All right. So cool. So yeah, so in this recursive summarization, I mean, essentially all we need to do is just take our sentences, right? We count the words in each of the sentences, right? We accumulate the total counts, and then we basically just kind of figure out, what we got to, right? Like how far we are along, and then use that to just divide sentences into chunks that are, up to 300 words, right? So the idea here is that we don't want to just like count 300 words or 3,000 words and then stop, right? Instead, what we want to do is we want to say, I want a whole sentence. I never want to break in the middle of a sentence. So just take up to the amount of time that I have, right? So essentially what we're doing here is really just kind of like coming up with the cumulative word counts, as we add in each sentence, and then, just breaking those up, right? Doing a group by list to group the sentences together, right? I like using a lot of these functions that use associations. But then at the end of the day, we just want the values, right? So we just kind of pull out the values in the association. And then, string riffle just takes those separate lists of sentences and puts them together as just a bunch of sentences concatenated, right? Just as kind of single strings.
I bluffed knowing concatenated from before, and from the context, I think I understand. But what does that actually mean?
Oh, it just means push them together. So we start out with let's say a list of 2 strings, and then we end up with 1 string that is joined, right? And so what string riffle does, it's a built-in function in Wolfram, is it just takes a list of strings and makes one big string with a space in between each of the pieces. I don't, there's probably a more elegant way to write this, but this is just the kind of the first thing that came to my mind as kind of a way to make individual chunks, right?
I know I say this in these interviews a lot, but if I could get students away from any idea in mathematics and science and whatever, it would be the idea, especially in mathematics, that they should be looking for the right way to do this. I hear people asking me that all the time in classrooms. It is such a toxic idea that says that there is one right way and any deviation from it makes it more and more wrong. And I just love the idea that the Wolfram language is built around, which is if it works and it doesn't cause problems, it's right.
Yeah, absolutely. I think as somebody that tries to teach students how to use Wolfram language, I think I often, for class materials, spend a lot of time trying to come up with the simplest, the most elegant way to do things. For these blog posts, I mean, it was just me drinking coffee, trying to hack around. So, it was really kind of more along the lines of whatever works.
Yeah.
That being said, I think a style that I like and that I think works well for these types of iterative explorations is, really just leaning into that sort of functional programming approach in the Wolfram language, right? I mean, it's a language that is very expressive. You can do procedural programming if you want, and lots of different things. But this idea of composing functions together is really useful. The other thing, I guess, that I just try to do personally because I aesthetically like it is I like to try to do everything using with instead of using module. Just because I find, well, first of all, it's a little bit faster. Usually that doesn't matter. But also the fact that, it essentially assigns a constant value. And so then you can't screw it up later on in your function. So, it just kind of makes the debugging, I find, just a little bit simpler. And it's often kind of a good heuristic clue, right? That like if you needed to define multiple things whose values change, maybe what you really want to do is define a few simple functions that you compose together instead of having some really big long function. So, I mean, I guess that's just sort of like a style that I find is useful.
No, I think
it's not always
good.
the right idea, but sometimes it's useful as a guide.
Yeah, I think it's great insight there, because a big part of figuring out how to do a project is often figuring out, okay, what functions am I going to need to define in order to make the final product, look clean and I can understand what it is that I'm doing. So that's great advice for people.
Yeah.
Go ahead.
If only for the reason that once you've done it like this, if something is going wrong, you can test the individual parts of your system and figure it out. If it's all just one cell that is an incredibly long, incredibly complex, possibly brilliant combination of code, and then it doesn't work, it's somewhere in there.
What are you going to do, right? And so, also as kind of an approach, right? Not shown here because I've deleted it, is often in the process of trying to debug. I mean, you just use that sort of interactive nature of the notebook, right? So you've got some test example, right? You can make sure that the little function does the thing that you want it to do. Just eyeball it, right? You don't have to write any formal tests, right? But that's kind of a good way to iteratively develop those small pieces and then put them together, right? And I always like to tell students, like, just solve a small problem first. Like, just solve one case, and then if you've got to apply it to a bunch of cases, then just apply the function that works on one case to all the cases, like using a map or something like that, right? So, all good ideas. I mean, here's how we.
Go ahead.
Oh yeah, sorry, Jason, go ahead.
I was just going to say it shows the parallels between writing and coding, and that just like in when you deal with writer's block, you sometimes just want to free write. And in what you've been describing is free coding. You're just getting things down, getting it out, not worrying about how it looks. If you were trying to teach stuff, of course, you may have a metric of best by being the shortest amount of lines, or well-functioning code, or if you're doing production stuff that you need to have tens of friends use, then you might need to worry about speed. But it's important just to jump in and get some stuff done, and the Wolfram language really helps with that.
That's right.
It's just impressive how science and coding and just writing can be so similar, even though so different.
Yeah, that is a really great analogy. So yeah, I mean, just to kind of show how this works, right? I mean,
and for anyone who's joining us right now, the summarization method that we've been talking about so far is to summarize parts of a long document and then summarize the group of summaries.
Absolutely right. So jumping in, right? I mean, the first thing we have to do is just divide things into chunks. So we define some function to do it, right? This is a function that satisfies, right? And then the actual summarization is actually, pretty straightforward, right? I mean, you get the whole corpus as a list of sentences, right? In this case, we're summarizing a State of the Union address, right? We use that chunking function that we defined to break it up, right? And so now we've got lists of chunks of sentences, right, that are not too long, and then we just apply this summarization function to that list of chunks, right? And what I'm doing here is actually applying the LLM function using parallel map, right? Because we want to apply the function to each chunk. It takes a few seconds to send the data to OpenAI and get the response back. And so we're just taking advantage of the fact that, we've got a few parallel processes to kind of like run a few of those at the same time. It's not really necessary. You could do it as a sequential map. But
although I do recommend doing it in the way that Josh has just described, because you'll be waiting quite a bit longer if you try to do them in sequence.
Yeah, I mean, 4 times as long on my home license.
Yeah. And that's especially a problem if you were trying to summarize something like a book as opposed to a State of the Union address.
That's right. And I guess if I can put in a wish list for the elves at Wolfram, it is certainly possible in the OpenAI API to run parallel calls. LLM synthesize and the sort of LLM resource function calls don't allow that in the current version, or it's like it's not kind of the way that it's implemented. But it's something that could be there in future issues. This is kind of a way around that. Just taking advantage of running these things in parallel. Yeah. So then we get back the results, right? We've got the summaries of each of these chunks, and then we just put all those summaries together and then divide them up into sentences, right? And now here's the part that's recursive, right? So we're actually going to run this process of summarizing chunks over our list of sentences as long as we exceed the word count, right? Because we wanted to get a summary that was below a total word count. So basically this kind of first stage, or running this process once, gives us a shorter document, right? We've summarized each of the individual pieces, but the sum of the summaries, right? The aggregate of the summaries may still be too long, right? And so essentially we just use the kind of nest while function in the Wolfram language to just repeat this process until we're below the desired word count. And then when we're done, we just put them back together, right? So, so that's the recursive part of this recursive summarization method. Again, we have a similar type of pattern, right? We just define a function that, returns true or false if we exceed the word count limit, right? And that's simple, right? We just take the sentences, we put them together, we count the words, we see if it's greater than, and that becomes our guard statement in this nest while. Yeah, so that's one strategy. And rather than just run this, I have kind of the result here. We wanted it to be below a certain number of words, and we ended up with something that was at like 210 words, and pretty much summarizes last year's State of the Union address, as I recall it to be. So that's one way to do it, right? Another strategy that you can use for summarization is what's called the refining method, right? And actually, this is a lot like the strategy that you had suggested, Noah, back at the beginning, right, when we were introducing this, right? So the idea is that we're just going to march through our text and summarize the first chunk, right? Like the first page of the book. We'll write a summary of that. We then say, summarize that summary plus the second page of the book, right? And now we'll get out a new summary, that is the summary of the first summary plus the summary of the second page, right? And then, we just keep marching on until we're all done with the total amount. So that's neat, right? It's kind of easier to implement. So maybe it's a thing that we would do first. But, a disadvantage is that it's a serial process, right? So we can't really take advantage of that parallelism, right? Like we just got to kind of march through chunk by chunk. People that study LLMs have also tried to kind of see what happens. And maybe there are like pros and cons associated with this type of method, right? Like you might lose some of the information in those initial parts. But again, it's another popular method of doing it, something that's totally reasonable. As you can see, it is pretty simple to implement, right?
Yeah.
So
Less
basically,
code involved.
Yeah, right. So what we're going to do, right? I mean, this is how we'll apply it, right? We have a list of the sentences, right? And our desired chunk length, right? How big is each page? We can just use that same chunking function that we wrote up above, right? So that's good, right? We've got a list of the chunks that we want to summarize. And then what we're going to do is we're going to fold this function over those chunks, right? So those of you that maybe aren't familiar with this sort of functional programming idea, right? What fold does in the Wolfram language is that it applies a function, right? In this case, this join summary function to an input value, right? And then we've got a kind of a new result that's present, right? We apply the function then to those two arguments and those two arguments and so on, right? And in fact, actually, I think the fold list explanation is a little bit clearer, right? So, our first iteration just gives us the value A, right? The first thing in our list, right? The second value gives us f of A and AB, right? Our next iteration gives us f of A, B, and C, and so on and so forth, right? So it's like folding it over each of those inputs, incorporating that next thing. And that's exactly the type of thing that we wanted to do, right, in this process.
Actually, I love that this is probably the most down-to-earth example of using folds that I've ever seen. Even though, yes, it's using an LLM at some part of the back-end process, which is, okay, fine, that's some fancy thing. But like, it just is an example of what fold can do. I love it.
Yeah. Oh, great. Yeah. I mean, hey, who knows? Maybe it'll be in the next fold documentation, right? So, the function that we're folding over, right, is this joined summary, right? And all we're going to do is we just have the previous summary as the first input and the current chunk, right, of new material that we want, right, as the second argument, right? Again, we just define a little constant, right, input, right, which is just take the previous summary and put it together with the chunk, right, the new chunk that we want it to do, and then we just send it to our LLM summarize, right? That's it, right? And then this will return that new summary, right, of that pair, and then we just use fold to repeat over that until we're out of chunks. And then when that's done, it just returns what the final value is, right? So yeah, it's really neat. We can see how well it does. It ends up being a bit more concise, but I think we could also play around with that a little bit.
Interesting.
Maybe setting some of the arguments about the summarization chunk sizes, and
that makes a bit of sense too, because in this situation, each summary of the original material has been summarized multiple times by the time it gets down to the end of it.
Yeah, that's right. And so
well, at least the ones from the beginning of the document have.
Yeah, that's right. So, a potential pathology in this type of strategy is that, you emphasize information that comes at the end.
Mhm.
And, unless there's something that really kind of catches the attention of the summarization function, you might lose some of those details that were mentioned early on.
As a homework assignment for people who are watching, a really fun thing you could do to iterate on this is to create a string template prompt. Maybe even add a couple of few shot examples of what you're supposed to, what it looks like to do a good job of taking a summary and appending a little bit, both in the case where it is highly relevant or in the case where maybe it's not relevant to what's good, and see for yourself, what the sort of differences are in ways that you could iterate on this sort of strategy.
Yeah, that's a really great idea. If someone wants to implement that, I'd certainly be interested to take a look, right? And there might be something to just kind of tack on as an add-on to this Wolfram community post.
Oh yeah.
Because I think that's a really
Which
nice
anyone can
illustration.
comment on. So
Anyone can comment on that. Absolutely. I guess we could talk about another strategy, right? And this one's kind of neat, right? I mean, the idea is that you actually combine summarization with topic modeling, right? And so the idea is that we're going to basically take this speech, we're going to divide it up into groups of 10 sentences each, right? And we're going to overlap them by 2 sentences each for continuity, right? So it's kind of like an overlapped list of things, right? So we take sentence 1 through 10, then we take sentence 8 through 18, we take sentence 16 through 26, and so on, and divide it up in that way. We're going to summarize each chunk, and we can do that just straight out of the run, right? Because they're only 10 sentences each. But then we're going to do something else, right? We're going to compute an embedding vector, right? That is like an internal representation of what that text means, right? It's a 768 dimensional vector, right?
oh my goodness.
That describes the internal state of the GPT model, right? And then what we'll do is, now those are just vectors. And so what we'll do is just cluster those embedding vectors, right? There are lots of different ways to do this, right? In the kind of example that I read about that uses a particular community detection algorithm, modularity optimization. You can do that using the find graph communities function in Wolfram. But you could use anything that you want to kind of summarize and cluster the entries, right? At this point, each of the individual chunks is just a vector in this 768 dimensional space. And so anything you can do to cluster vectors is something that you can use. All right, so here we go. I'm just going to demonstrate this for like one round, right? I guess kind of showing this idea of like, just build a function that does it for one thing and then put it together, right? So we want it to chunk by sentences instead of word count. So we need a new chunking function here, right? We take our list of sentences, right? We have our chunk size and our overlap. And actually, you can do this just using the partition function that is built into Wolfram, right? So we say partition the sentences, they should be up to a particular chunk size, right? Like we might not have a complete multiple at the end. So up to just allows us for the last few to kind of be below our chunk size. And then, we want it to be offset by the chunk size minus the overlap, right? So that just kind of marches through and gives us that sort of 1 through 10, 8 through 18, 16 through 26, and so on, right? That's it. So that splits it up, and then we just use a string riffle to put those sentences together into individual strings, right? So that's one little thing that we have to do. Then the first step is we generate the summaries for each chunk, right? And we've already seen how to do that, right? So we split them up into the chunks. We just use parallel map to then generate the summaries for each of those 10 sentence chunks. And here I just saved this because I didn't want to redo it. It takes a minute or two to do. So let me just retrieve the ones that I had from before so we can play around with them. The next thing that we need to do is generate the embeddings, right? And so you can do this with the kind of the default Wolfram language support. You have to use the OpenAI service connection. So there's not like a function like LLM synthesize for embeddings. It's kind of baked into the OpenAI service connection.
Yeah, and
but
you can access that either through doing the Christopher Wolfram OpenAI link, as Josh is showing here, or also as Josh was saying, the service connect and then service execute. Yeah. So yep.
And I have to say, like, back when I was trying to figure this out in August, I hadn't figured out the service execute, OpenAI service execute stuff. So I just used the Christopher Wolfram's OpenAI link, and that defines a function, OpenAI embedding, that will make the calls and compute the embeddings, right? I think now that I've discovered the service execute, it is actually a bit more powerful, right? Because it actually allows you to request multiple embeddings simultaneously in parallel, although it's limited to about 20. Anyway, it's kind of small detail, but these
another. Oh, sorry.
equal ways to do it. Yeah. Oh, go ahead.
Sorry.
John.
I was just going to say, also stay tuned for things coming up with being able to register services in upcoming version, because we're in a sort of phase of technology going on in the world where there's interesting new things that you might want to service connect to all the time. And so, you might be interested in some mechanism of, oh, there's a service, there isn't like an official function for it yet. Maybe I don't want to worry about writing HTTP requests because, you can do that, but that can be, not necessarily the most elegant way. And so maybe you want to create some service request that, isn't one of the predefined things. So stay tuned, everyone, for things going on with service connections that should help in some of the things that Josh was figuring out a while ago. That I agree. There's actually some times where I do resort to writing either the service connect or the HTTP request, depending on some specific little corner case I might want to do.
Yeah, no, that's really great to know, John. I think that'll be super powerful, right? Because so many of these really powerful services provide REST APIs, right? And so having a kind of a really convenient way of working with that is going to be super empowering for people. So anyway, at the end of the day, I mean, but if you just use OpenAI link, right, you could kind of generate all your embeddings. Doesn't take too long. It might cost you about a nickel to run this experiment. And what you end up doing is that you end up kind of getting a list of these 768 dimensional vectors, right, for each of these 10-sentence chunks. Actually, just to visualize this, I use distance matrix, and we're just using the cosine distance, right? So that's kind of like, that's just the dot product of two vectors. That's kind of like the standard way that people try to look for similarities in these embedding vectors out in the community, right? And so we can see that, like, yeah, every chunk is exactly the same as itself. So, the diagonals have the highest values.
0.
Yeah, and then it falls off. But, what's neat is that you can kind of see that there are like thematic, semantic relationships between sentences that are not next to one another, right? So the kind of lighter areas are areas that are kind of like semantically more related to one another. And so what we're going to do in this approach is essentially just cluster them, right? So we could just use, the find clusters function built into Wolfram, right? We're actually going to do a little trick here, right? So we're clustering by the embeddings, but the value that we want are actually the summaries that are close to one another. So if you just use this embeddings goes to summaries, find clusters will return the word chunks that are similar, but after they've been clustered by the vector similarity, right, as measured by the cosine distance. And so then that gives us things that are related to one another, and we just put those strings together, right, using string riffle.
Okay. So the summary will be talking about similar things in the same area, as opposed to talking about topic A, then topic B, then topic A again in some weird sort of fragmented way.
Yeah, that's exactly right. So, like, for example, like in these chunks, I'm actually, rather than like putting the text together, which would be too much, right? We just say, like, yeah, chunks, 1, 2, and 23 were all kind of thematically related to one another, right? Like the words had a semantic relationship to one another as defined by the GPT model, right? So those should all go together, right? chunks 3 and 42 had some relationship to one another, right? Chunks 4, 5, 6, 8, 9, 11, 13, etc., right? We're related to another. So what find clusters is doing is essentially saying, yeah, these are these things where like those vectors are all kind of like near one another in this 768 dimensional space. And so, we should kind of put those together, right? And I think I counted also like, if we look at these chunks, like there's a pretty big set of passages that all are supposed to go together, right? We might be worried that that's too many words, but it turns out it's not too much, right? It's only like 1,300 words. So, if we were writing production code, we might want to think about that edge case, but just for the purpose of hacking, it was good enough. So, essentially all we have to do, right, having kind of demonstrated that like each of the pieces, right, what we're going to do is just define a function, right? We get a list of sentences, right, in our document, right? We generate the summaries as we demonstrated up above, right, by breaking them up into these overlapping blocks of 10. We compute the embeddings as we demonstrated above, in this case, using the Christopher Wolfram package. We find the clusters, right, as demonstrated above, and then we return a list of the kind of the new chunks of things that should be all together, right? So that's it. That's one iteration through this process. And so then what we'll do is we'll then just, again, use this sort of functional programming model, right? Where we're going to run this process of summarizing the clusters we start with all the sentences, but in the next iteration, we've got the summaries that have been grouped together and summarized together in appropriate chunks. And we just repeat this until we no longer exceed the word count, right? So that's it, right? And then when we're all done, we've got this list of kind of summaries that we put together. We just stitch them together with string riffle. And so, we can just see what that ends up giving us, right? Oh, hang on a second. There we go. So, I mean, this gives us a summary, and actually, it keeps a lot more of the details together in this summary, right? Because it's essentially said, yeah, like these were things that were disconnected in time in the speech, right? But they were themes that should have gone together. And when I put them together, then I realized like that's actually an important theme in the speech, right? It's something I should keep.
This is fascinating. I want to say, first of all, that I can't believe this is what you do when you're idly curious in your free time about something. This is amazing. I do want to ask, though, do we have some more examples that are a little more chemistry specific, maybe in terms of either stuff that you're teaching or stuff that you're doing in research or anything like that?
Sure. I guess I could. One thing that I think is, well, I'll tell you about one thing that is related to research that I just think is really neat, right? Maybe going a little bit off script, right? So there's an idea of tool use in these large language models, right? So the idea is that the large language models don't know how to do precise calculations, right? But they can call other tools to do those calculations, tools that are defined by computer programs. And those of you that have used Wolfram Alpha as a plugin within ChatGPT have seen how this works, right? ChatGPT calls Wolfram Alpha that then does some calculation. And so I was really inspired by a research paper that I saw called ChemCrow. And these were some chemists that said, hey, I've got an LLM. Can I add in some chemistry-specific tools that the LLM can use to perform calculations that it needs? So when I first read this paper, it sounded really hard. But it turns out it's actually super easy to implement this in the Wolfram language. So, in fact, I'll show you this in like 3 minutes, right? So, just as an example, right? Like here's some molecule, right? And, this is all default Wolfram language code, right? That takes the name of a molecule and computes a standard identifier known as a smile string, or computes the molar mass, right? Something you might do in high school chemistry. ChatGPT doesn't really know how to handle complicated molecules like this. And so, if you ask it, what's the smile string, it just gives you like the wrong molecule, right? So that's weird, right? And so basically what you can do in the Wolfram language that is really powerful is you can just define a tool for your LLM, right? It's just LLM tool, right? The first argument is the tool name, right? So I'm just going to call it name to smiles, right? The second argument, or I guess the second argument is the second entry in a list, right? So this is actually a description of what that tool does that we're going to tell our GPT model, right? So this is what I do, right? This is my name and this is what I do, right? Our next argument is actually the input parameter variable, right? I'm just going to call it name because I couldn't think of anything better. And then the last argument is the function that you actually want to perform, right? And this is something that the Wolfram language actually knows how to do, right? And so then you can use this tool in LLM synthesize really easily, right? You just provide it as an input to your LLM evaluator option, right? And so now when we ask this, oh, I guess it would help if I define this function. I'm living dangerously here. So now when we define this, what the LLM is going to do is it's going to say, hey, I've got this tool that I know converts a given chemical name to its corresponding smiles representation. I need to use that to solve this problem. Okay, I'm going to go and ask the Wolfram language implementation running on my laptop how to do it. And then I'll incorporate that result and return the value, right? And so what's really powerful is that actually out of the box, models like GPT-4 know how to put multiple tools together, right? So, again, I'm just going to define 2 more tools that were in the ChemCrow paper. They're like one-liners in the Wolfram language, right? Like, here's a tool that calculates the molecular weight given one of these standard identifiers, right? Here's a tool that uses a resource function to pull something up. And so, without this tool, GPT runs through some calculation, all the numbers are wrong. It fails the Gen Chem final exam, right? But with the tool, right, we can ask the same question, right? And we can tell the model, like, use the tools that are available. Even if you don't, it's smart enough to use the tools that are available. And it stitches together those intermediate results and gives you the right answer, right? By actually doing, a calculation using the Wolfram kernel running on your own computer. So it's kind of like having a little back and forth interchange with the program that you've written.
Thank you so much for this example. I mean, I think it's quite clear to people who follow, using LLMs for research applications or for more than, let's say, writing an essay for you, that the ability for them to call functions and use tools and tap in when they want to have an actual computation done, and they do so in a fairly intelligent way, especially with the right prompting, is really one of the most exciting things about them.
It is really cool. And, and I have to say, I mean, first of all, the ChemCrow work is really neat. And they have a lot of fancier tools that aren't just one-liners, right? That do things like try to figure out a chain of chemical reactions that solve a problem and so on. These were just a few really kind of like, basic things that they did, but that are really, really kind of powerful, right? And yeah, and I agree. I mean, when I first kind of learned about tool use, it seemed like something that was really complicated. And, and I hope this example is maybe one for the listeners on, how they can think about, taking those pieces of the calculation that are easy to do and easy to define a program for, and, giving that as a capability to an LLM to work with, where the input to the LLM might be a little bit messier and kind of uncertain. And, there are applications, of course, far beyond chemistry. But, this is one that I thought was really kind of neat.
That is amazing. And another one of the things that I know that you're very passionate about as well is chemical education. And so we'd love to also get into this topic with you today.
Sure. Well, I mean, that's another community post, right? And this was actually a paper that we put out just this past fall in the Journal of Chemical Education. And after testing it on a group of first-year general chemistry students who volunteered, the graphical table of content image was made by generative AI, and we put that in the acknowledgments, by the way, right? So, we're not, trying to slip one over, right? And this was actually work with my good friend and collaborator, Alex Norquist at Haverford College. And then a bunch of undergraduate students, Gabe Jones-Thompson, Kaching He, and Thomas Egg, who, both, Gabe and Kaching really kind of worked on developing the experimental side of the laboratory. And Tom also worked on the kind of computational materials and teaching materials. And the idea here is really kind of like to bring some of the things that I like in my research, right? Laboratory automation, using robots to perform chemical reactions, and data science methods, and to try to see if we could bring that to the kind of first year chemistry classroom, right? We don't want to, get rid of general chemistry, right? We're always going to have general chemistry class, but
Sure.
the idea is, can we take some of the labs that we have in a general chemistry class and that other people have in labs in general chemistry class and re-envision them, right, as kind of involving using robots to perform reactions, and using some computational tools, right, in Wolfram, for example, to do a data analysis. And in a way, they're really synergistic, right? Because we, with the lab automation, the students are now performing 100 experiments in 30 minutes, right? And so now they've got to make sense of that data. They can't do it in Microsoft Excel or just by hand with a calculator like they're used to. They really need kind of a computational environment to be able to make this work. So I mean, basically, the thing that we did was, and these are all kind of like materials that are in a community post, right? Is we wanted to teach these ideas, right? Introduce some programming in Mathematica, right?
Mhm.
In kind of a notebook environment. It turns out that like half of our students have already used Mathematica by the time they come into this lab. They've used it in their math classes, right? So that's kind of it makes it a little bit of a softer start. And what we have them do is kind of work through, there's a pre-lab notebook that they work through on their own, right? It includes basic things like, how do you use the Mathematica interface? And like, what are variables and functions and things, right? And then in that pre-lab exercise, they kind of work through some interactive pieces, right? That are, again, just written in the Wolfram language to understand some of the basic physical ideas, right? So we have this idea of sort of understanding mixtures in a geometric form, right? And kind of understanding, like, if I mix solutions A and B together and they have different species present, that's like a point in this concentration space that we call it. So they've got some interactive exercises to work on that and to kind of think about and think through. We then kind of introduce this idea of like, well, how would you write a function that could maybe convert concentration to volumes, right? Because when you go into the lab, or maybe for this audience, when you're making a martini, right? You don't specify what the concentration is of alcohol in your final martini. You specify, well, I have 3 parts of gin and 1 part of vermouth, right? So you do everything in terms of volume fractions in the lab, but you want to think about it in terms of concentration.
Yeah,
and so,
makes sense. Nobody's pouring by moles.
Yeah, that's
No.
right. That's exactly right. So, we kind of walk them through just kind of thinking about this and some simple ways. There are also some hints. You're like, hey, maybe you're taking linear algebra. Doesn't this look a lot like linear algebra, right? As kind of a wink to students that maybe have a little bit more. And then the thing that we do is, we can kind of use this to kind of walk through the idea of like, what are the mixtures that are possible, right? Like if I mix 2 things, I can never get something that is more concentrated than what I started out with, right? And so, mathematically, what that defines is a convex hull.
Unless I
right?
suppose it causes some sort of huge evaporation thing to happen.
Yeah, I mean,
Yeah,
that
but
would
that's a
be
different
sort of an edge
process.
case,
Mhm,
right?
mhm.
Yeah.
So we'll leave that we'll leave that edge case out, right?
Yeah.
But yeah, so basically we kind of walk them through this idea, and then a possible experiment is just a point within this region, right? So there's actually something really nice about thinking about mixtures in this way as these convex combinations, right? The convex hull of your stock solutions defines the possible spaces of mixtures, and then you just sample random points within that space, right? It's really kind of like a kind of a neat and really kind of powerful way of thinking about mixtures, right? But this allows students to kind of like generate randomly generated experiments, right?
Hmm.
In this space. And then we walk them through, kind of thinking about, like, how do you think about chemical equilibrium in this concentration space, right? Well, by the way, you just do a little algebra, right? You take your equilibrium expression and divide both sides by x, right? And this then kind of allows us to kind of think about this, right? The gray triangle are possible mixtures, right? That could be made. Blue are maybe some random experiments. And this red line indicates the equilibrium, right? And so everything above this line is something where the reaction is going to produce a solid product, in this case, right? We're precipitating lead iodide. Everything below the line is subsaturated, right? So it's not going to produce a solid product, right?
So in essence, this is a phase diagram.
Yeah, that's right. It's sort of a phase diagram in units of concentration instead of in pressure and temperature.
Sorry if you said this already, but what do the axes represent?
Oh, so the axes here are just the concentration of chemical species X and chemical species Y. So in the experiment that the students are actually going to do, it'll be lead and iodide, right? And so they'll precipitate out a lead iodide solid, right? That's it, right? So, I mean, the thing that we want students to play around with is this idea that, like, let's say you do an experiment, right? You've generated some random points, right, in concentrations of lead and concentrations of iodine, right? Now we're using real data. You observe that you formed a precipitate for the red points, right? Like you're making a yellow lead iodide crystal on the bottom of your container, right? And in the black points, no reaction has occurred, right? It's just a clear solution, right? And so, the thing that you can think about doing then is trying to, like, you've got this equilibrium equation, and, by changing your equilibrium constant, right? The goal is to try to find a value of that equilibrium constant that is, perfectly divides the two outcomes, right? Because that's really the boundary. Anything above that equilibrium curve is supersaturated, right? And will form a product. And everything below is not saturated enough to form a product, right? So, this is a way of maybe kind of turning around the problem that you would typically do in a Gen Chem lab, where you do some, like, tedious set of titrations, right? And try to, like, just march along this red curve. Instead, we just say to the students, perform a bunch of reactions, right? Observe these discrete outcomes, like there's a yellow crystal at the bottom, that's a red point, or not, right? And then I can find where the equilibrium curve is by just fitting a dividing surface, right? Finding the kind of the value that best separates things that precipitate or not.
I've said off air, but I'll say it again, that, had my chemistry education been this interactive and, this presentation of things like equilibrium constants, I might have, been more interested in going into chemistry instead of other sciences. This is fantastic.
If only we had a time machine as a program.
There's still time for you to switch.
Yeah,
that's true.
You can see the light.
Lifelong learning is definitely an important thing for all to keep in mind.
Absolutely. So, of course, I'm just kind of running through this pretty quickly in the interest of time. There's kind of more to describe. It turns out that if you take a logarithm, then it just becomes like a kind of a linear problem. And then that actually is exactly a logistic regression problem, right? So we turn this problem of finding an equilibrium constant into a logistic regression problem. And then, just use Wolfram language to fit that logistic regression problem, right? Where we're trying to find this dividing surface. So we kind of walk students through doing that. And then we say, all right, great. Well, you've kind of worked through this fake example. Now it's your turn. We want you to generate some experiments, right? And, we're going to run them on a robot, right? In the lab. In fact, you're going to run them in the lab on the robot yourself. So basically what we do is we have the students generate, a list of experiments, right? They generate, a kind of a 96 experiments each. We then have them do 24 of those experiments by hand. It's really tedious and annoying, right? But they actually learn some useful skills, right, of using a micropipetter. And then we bring in students in pairs to work on the robot, right? And so they take these machine instructions that they've generated. We show them how to use this liquid dispensing robot, and then they fire it off and they run the reactions. And then, the reaction actually takes about 24 hours to occur, right? It's a little bit slow. So they set everything up and then, just put the setup that they made aside. And then we have the TAs just go through and take a digital photo and dispose of everything. There is some lead that is involved. So, it's just nicer to have the TAs do it. But yeah, and then, this is the sort of the pre-lab. There's also a post-lab notebook that we have students run through that really says like, okay, great, start with importing your data. And now let's work with that data, right? Let's analyze your results. Essentially, it's like items 7, 8, and 9 in this list, right? They perform the experiments, they read the results in, they do some visualization, and then they find the equilibrium constants. And then, it turns out that the values that they get are going to be different from the ones that they did by hand. And so we have them kind of analyze that and think about sources of error. We also have them aggregate all their experiments. So, we had 14 students running this. So there were 7 batches of experiments. Each pair of students ran about 100 reactions. So they have, 700, 800 reactions to analyze in aggregate. And so now they can really start to see, statistical properties emerging and get a sense of like, what are the variations? And, as soon as they've got 100 experiments to analyze, there's no way that they're going to do this by hand, right? And, fitting a logistic function is not something that they can do in Excel either. So, it really kind of motivates using some of these tools. Logistic regression is kind of like the first thing that you learn in a machine learning class, right? Maybe after linear regression, kind of related thing. So, the goal is to kind of expose students to this idea and just plant the seed that like automation is relevant to chemistry. Data science is relevant to chemistry. And what was really neat, you can kind of read more about it in this paper that we wrote. I mean, we surveyed students at the beginning of the class. All of them knew that automation and robots existed. Some of them had even like built robots in high school. All of them knew that machine learning and data science were things that existed, but only 1 out of 14 students knew that you could apply those ideas to chemistry. After the fact, they all knew that you could do it, and most of them really liked the idea, right? So, hopefully we're kind of training a generation of students, right? Some of them will be chemists, some of them will be biologists, some of them will be physicians, right? Who know that like data science and automation are things that are relevant to scientific problems, right? And they've even gotten a chance to get their hands dirty in the lab and get their hands dirty on the keyboard, programming some of these things and building them up.
They'll be ready to use the laboratory of tomorrow, which is actually arguably driven by a Mathematica notebook. If you're familiar with the Emerald Cloud Lab,
I very much
where
am.
you can just write your experiments in a Wolfram notebook and run it. So it's really cool.
It's really exciting technology, and and I think as that becomes more accessible and affordable, it's really fun to think about how do we integrate that into education. And I know our friends at Carnegie Mellon University are kind of pushing that forward. This lab, even though we didn't use the Emerald Cloud Lab to perform it, we had the students actually go in and do the experiments themselves, is absolutely something that would transfer really smoothly into that sort of cloud lab type environment.
This is beautiful. I've got, I'm sorry, did you have more you wanted to say there about
No, I think I could just stop right there.
Okay. Now, I've got a question from the community coming in asking, and this might have been the regression that you were talking about, but I do want to double check the division between saturated and unsaturated. Is that just something that they would try and guess by eyeballing it, or was there actually an algorithmic approach to
Oh,
finding the
yeah.
division there?
Yeah, sorry to run through that so
I mean,
quickly.
I'm glad you're getting so much in on this time.
But yeah, so what we wanted to do was like we have them actually try to just kind of like use the slider bar and the interactives to get a feel for it. But in the end, yeah, actually we have them do a logistic regression.
And that's the regression you were talking about.
Using logit model fit. So they actually do it, they first do it kind of like in the loosey-goosey interactive way to get a feel. But then we say, you really don't want to do this, right? And by the way, like, how are you going to make a disciplined choice? Like, there's going to be experimental error. You're not going to find a perfect dividing surface. You could eyeball it and make a guess, or we have kind of a well-defined algorithm that will do it. So in the end, yes, they use logit model fit to find the best parameters and do the calculations on those parameters and come up with the final result. We also show them how to add some extra constraints, like there are different variations of it that we walk them through. But the goal was like give them something to play with interactively first, just to get the intuition, right? The kind of the fingertip feel, and then show them how to do it interactively. And the same thing with the concentration space, right? Like we have these kind of interactive exercises just to get a feel of how those mixtures work. And then we say, well, actually, you just want to do it as an equation solving thing. Here's how you solve it as an equation, right? So the idea is to also kind of provide kind of like a multimodal learning experience, right?
Yep.
If you like fiddling around with things, fiddle around with things. And if you like writing a program, write a program. Ultimately, we want everybody to do both so they can make those connections for themselves.
This ties exactly into the second thing that I was going to ask you about, which is that I love how there's such a combination in these examples of you saying, I have a tool which does a particular thing very well. How can I change what I'm doing into that particular thing so it will be successful? And other examples where you have things like fold, where you say, I want to do this particular thing. What is a built-in function that will do exactly that sort of thing for me? And so I wanted to ask you, in either research or teaching or whatever, which of those experiences do you most often find yourself having when you're working with these tools?
Oh, gee. I think, I've been programming since I was 5 years old, and that was a long time ago. Not in Wolfram language, in BASIC, right? But but that was a long time ago, right? And I've programmed all sorts of different languages, supercomputers, 25-cent microcontrollers. So I mean, I guess I'm at a certain stage where I generally have an idea of, hey, this is something that I want to do as a functional fold, and I need a function that I can fold over. Let me implement that function, right? So I mean, I guess like for myself as just a kind of an implementer of things, I've usually got a pretty good mental model of how to break up the problems, and I just start at the smallest layer and build upwards, right?
We had an
but
audience
it's because I've been
question.
around the block a few times, right?
Sure.
As to your question of like kind of finding things that are built into the language that work. I mean, I think my old practice was like just reading the documentation and kind of searching the documentation. But I think now actually using the chat notebooks is really powerful, right? Because you could just open up a chat notebook session and say, hey, this is the thing that I want to do. And it's often not the way that I would implement it, but it tells you what are good functions that you might use.
I'm glad you mentioned that, because we just had one audience question related to that, which is, how do you help students, if there's any kind of a learning curve in getting into the coding initially? So that's a great answer to that question. Another audience question that we just had has to do with, so is this a general chemistry course? Because we mentioned students who are thinking about going into biology or physicians or things like this, but it's also important, as you well know, for students who knows what they're interested in doing. And so yeah, so the question was, how did those students like this sort of approach? Did that connect as well as I would expect just from like an education theory level it did? But what were your actual experiences with students that might not be interested in going into chemistry, but were still doing this experience?
Sure, right. I mean, I think that's so that's, first of all, that's a really great question. This is kind of a new thing, right? So in the past, one of the things that I had worked on, right, was trying to incorporate more of this sort of programming and machine learning topics into our advanced chemistry courses, right? Like junior level chemistry courses, right?
Mm-hmm.
I even wrote a book on essentially how to implement all these basic models of physical chemistry in the Wolfram language, right? Christmas is coming in case anyone's looking for a gift idea. But this idea of trying to work things into the general chemistry curriculum is brand new, right? I mean, we just tried it this past spring, right? So this is really brand new. All of those students are like sophomores now. So, so we don't know how they've gone on in their career trajectory. But I think something that's really exciting about working these ideas early into the curriculum is that you do get the broadest cross-section of students, right? The students that take general chemistry, might want to go into the sciences, any one of the sciences. They might want to go to medical school. They might decide, hey, this is not for me. And, but yeah, I think the thing that we can do is kind of introduce them to some tools, some ways of thinking about the world, computational thinking, right? And that's something that is really generalizable and can take you in lots of different directions.
Yeah.
I also teach a course for non-science majors on drug discovery and computational drug discovery. It's also a writing intensive course, and it's a chemistry course, so we have to have labs. They're all computational labs, and so we do some basic Wolfram language chem informatics things. We also do some protein docking, drug docking calculations. And that's an audience of students that are like not at all science majors, right? This is a class that doesn't satisfy your requirements as a science major, right? They're often philosophy majors or English majors or whatnot. And those students really get a lot out of the sort of computational thinking type skills because it's something that at the time they say, gee, this is really kind of hard. It's really different. And then later on in their coursework, they come up with something, a problem, that they say, oh, gee, if only I knew how to calculate a net present value. Oh, wait, we did that in Schrier's class, right? Like, let me dig back in and try to do this. Or, gee, I've got this data set of psychrometric things that I need to plot and fit. If only I knew, oh, wait, I did that before. So yeah, so I think in a lot of cases, we're especially as we put these things early on in the curriculum, we're really planting seeds, and students can take that in lots of different directions. I've got one student who actually I think I'm going to meet with in 6 minutes, who was a student in that class, and maybe partially as a result of that, decided that he really wanted to get into mathematics and data science, and is now playing around with LLMs for different things. And so, yeah, so you never know kind of like the way that students are going to take things. But I think if we give them some more tools in their toolbox, it only helps them, right?
I love this because a question that is so often seen as confrontational in education is, when are we ever going to use this? Is looking at something that you're being taught and responding by saying, I have no idea how this is going to connect to anything outside of this class. And it sounds like the answer to that in this particular case is absolutely anywhere and wherever you want to, because all of these things are things that could be applied so much more broadly than just the particular problem they're being used on.
Yeah. And maybe that's an exciting opportunity for, especially with these sort of LLMs, is, they give us sort of a bridge between the messy, unstructured world of natural language and computable data, right? Things that we can perform computations on, right? If I've just got the State of the Union address, it's not clear how I say that like particular parts of that are related to one another, right? But what the LLM lets me do is it lets me turn that into a vector, and then I can see what parts are related. And as applied mathematicians and friends of applied mathematicians, we know a bag of tricks. But that bag of tricks now becomes relevant to the political science student that wants to analyze this, or the English major, right, that wants to understand things. So I think it's really kind of exciting. And I think, my colleagues in the humanities and the social sciences are probably having lots of fun thinking about how to incorporate some of these tools there. I'm not having that fun because I'm on sabbatical. So
So I know you have 2 minutes left until you've got a meeting to get to, roughly speaking. So just real quick food for thought. If there's any other things that Jason, you'd like to just put out into the thing, maybe we can do a follow-up stream if there's any other ideas that we didn't get a chance to get to today. But thank you so much for being here as well.
My only comment is just to follow up on what Josh was saying. In chemistry, we have a long history of incorporating technology into the classroom. We've been there's groups like the Molecule Consortium in the Mid-Atlantic area that have been building computational chemistry activities using research level tools in general chemistry. And that's been ongoing for 30 years. And the same arguments for getting students involved with those calculations, or the same thing like an analytical chemistry course, getting them to touch the actual instruments that they'll be using in the real world when they leave the institution, it has a long history. So I think this is just yet the next iteration of using LLMs and using machine learning and using notebooks, which have been around for quite a while, electronic notebooks. So it's very exciting to see how it all interconnects and just contributes to a long history of good chemical education.
With just a little bit of time left, we've got another audience question, which I always love to see, so I'm going to throw it into the mix.
Yeah.
The question was specifically about drug discovery, but I'm going to throw it out even wider, but saying for drug discovery or anything else on your mind, how do you think LLMs are going to change that?
Oh my. Well, we might need another live stream for that.
I'm definitely getting the impression from audience questions that we might need to do a follow-up because there's a lot of interest. So
all right, just to give the TLDR version of this, there's actually a tremendous amount of work in using machine learning and even using LLMs to assist in drug discovery and things related to human health. A few buddies of mine to mention, right, include folks at futurehouse.org, which is kind of an organization funded by the Schmidt Foundation. Just over the past weekend, they used kind of an LLM RAG-based system to write Wikipedia entries on 18,000 human genes that didn't have a Wikipedia entry based on scientific literature. It does just as good as humans. They checked. And now we have complete Wikipedia entries for every expressed protein in humans.
Beautiful.
That's an enabling technology for basic research. The major pharmaceutical companies, also have efforts in doing this. Some of our friends in New York City at Prescient, right, which is a kind of a exploratory R&D organization that's part of Merck, come to mind, right, as people that are really kind of using this type of technology to advance human health.
Wonderful.
There are
a
many,
lot to look
many
forward to. A lot to look forward to. Well, thank you so much for your time. Thank you, everyone who's joined us today. I'm looking forward to hearing more and reading more of that notebook. I know we didn't get to all of it. Thank you so much.
My pleasure. It's really fun being with all of you today.